Welcome to the 17th lecture for the series Trends in Modern Cryptography. I am Riccardo Longo from the University of Trento, and I will talk about key policy attribute-based encryption. So, you should already have seen something about attribute-based encryption, but I will do a brief recap anyway. So, the main idea is to include an access policy in the encryption scheme, where policies are represented by Boolean formulas involving AND or NOT and threshold operations on some attributes. There are two main models: ciphertext policy attribute-based encryption that you should already have seen, where the policy is embedded in the ciphertext and users are described by attributes. Today we will see key policy attribute-based encryption, where the policy is embedded in the decryption key and ciphertexts are described by attributes. So let's start with an example. Let's suppose that we are running a streaming service where we want to offer subscription plans when the user can choose whatever he wants to see. So let us have a user that wants to watch all of Game of Thrones. Then the first episode of the first season of every show there is, so to decide whether to watch it or not. And the first 3 seasons of NCIS. We have the policy described by this tree, where we have that each internal node is a threshold value that describes how many of the subtrees must be satisfied in order for the node to be satisfied. So when we have a 1, we have an OR. When we have a 2 with 2 children, then it is an AND. If we have an intermediate value, then it's a threshold. So we have, starting from the right, 2 out of season 1 and episode 1. It means that we want the ciphertext to be described both by season 1 and episode 1. Then Game of Thrones is simply an attribute, the name of the show. Then we have another subtree that is 2 out of NCIS. So we have an AND that must be NCIS, and 1 among season 1, season 2, and season 3. So this is any episode of the first 3 seasons of NCIS. We have a 1 at the top, so this is an OR. So if one of these conditions is satisfied, we have our policy satisfied. Let's see an example. We have 2 files, Game of Thrones season 3, episode 9, and Stargate SG-1, season 1, episode 12. For the first file, we can see that the attribute Game of Thrones satisfied by itself the whole tree. So the policy is satisfied. Note that the attribute season 3 satisfies this subtree, but the upper levels tree is not satisfied because it requires also the attribute NCIS. But we don't care because we already have the attribute Game of Thrones satisfied. The second file, we have that no tree is satisfied. We have only this subtree because season 1 satisfies this subtree, but we do not have the attribute NCIS, so this is not satisfied. We do not have the attribute episode 1, so this is not satisfied. And we don't have neither of the subtrees nor Game of Thrones, so the access policy is not satisfied. So to recap, we have that the first attribute set satisfies the access policy, the second does not. So let's see how we can build an attribute, a key policy attribute-based encryption scheme. let's recap the basics. We need, of course, pairing. There is not this is not the only method, but this is the main method to build them. So let's recap what is a pairing and what are bilinear groups. Let us have two groups, G1 and G2, and let us suppose they are the same order P, and that E be a pairing. This is a bilinear map from G1 times itself to G2 with the following properties. Linearity, that means for two elements G and H of G1 and two elements A and B of ZP, we have that the exponents basically can be taken outside. So in particular, this means that also we can swap the exponents inside, because this holds for every value of A and B. Then we need non-degeneracy. This means that if G is a generator of G1, the pairing of G with itself is not the identity of the group G2. Note that this is a simplification of pairing and bilinear groups, because we have also other types of pairing that operate with different groups. This is a symmetric pairing because we have the same group in both positions of the pairing. But this simplification is useful for our purposes. Then we call G1 bilinear group if the group operations in G1 and G2 and the bilinear map E are efficiently computable. In practice, the groups are built according to a security parameter K that will determine how difficult are the problems and to operate in this group. What is the main security assumptions that we need for our construction? It is the decisional bilinear Diffie-Hellman problem. Let us recap how this problem is defined. We have 4 exponents, A, B, C, and R in ZP, that are chosen at random, and a generator G of the bilinear group G1. Then an instance of the problem is given by the values G2A, G2B, and G2C, and an element T. And we want to build an algorithm B that distinguishes the form of the element T. That is, we want to distinguish whether this element T is of the form pairing of G with itself elevated to ABC, or the pairing of G with itself elevated to R. And we will output respectively 1 and 0. So the advantage of B is defined as basically how well it performs against a random. That is the probability of guessing right, basically, where the probability is taken over all the random choices taken, that is a generator, the exponents, and the possible random bits that are consumed by the algorithm B itself. The assumption that we need is that there is no probabilistic polynomial time algorithm B that has more than negligible advantage. This, in practice, means that an element of the form of pairing G with itself to ABC is indistinguishable from a random element of the target group G2. Okay. Let us see something more on access structures. We define an access structure given a universe of attributes U, the set of subsets of the universe U that are authorized. That is, a set of attributes S satisfies the policy described by A if and only if this set S is contained in the access structure A. This access structure is monotonic if basically more attributes we have, more authorized we are. That is, given two subsets, S0 and S1. with S0 containing S1, then if S0 is authorized for the access to the structure A, then so is S1. Of course, this means that if we construct the policies using only AND, OR, and threshold operators, that is, we exclude the NOT logical operation, then we have a monotonic access structure. In fact, it's easily seen that if we do not use NOT, more attributes we have, more authorized we are. Okay. Why do we restrict to monotonic access structures? Because they have a very, very nice property. That is, that it can be translated into linear secret sharing schemes. And this translation is efficient. A linear secret sharing scheme is permits to share a secret between parties, such that only sets of parties that are authorized according to the access structure can reconstruct this secret. And this reconstruction uses only linear operations, and it can be done without knowing any secret value. So to define a linear secret sharing scheme, we need a set of parties P, a shared generating matrix M, and we will define L times N and its dimensions. We work always on over ZP, and a function rho that associates every row Mi of the matrix to the party rho I in P for all the rows. That is, we associate to every row of the shared generating matrix a party. Then, when we want to share a secret, we simply start from a vector V that has our secret to be shared in the first position, and the other positions are filled with random elements. And we multiply this vector by the matrix M. Then we obtain a vector of shares lambda, and we distribute the shares according to the labeling function rho. That is, the share lambda I will be given to the party rho of I. Then we have the nice property that is, if S is an authorized set, then we can find a subset I of the rows of the shared generating matrix, such that we can interpolate the shares lambda I with constants wi, and these constants are publicly computable, given only the set I. And with this interpolation, linear interpolation, we can reconstruct the secret S. So, given the access structure, we can find the subset I, and given the subset I, we can define the constants wi, and if we have the shares lambda I corresponding to this interpolating set, we can reconstruct the secret. And the important thing is that if we do not have lambda i's for a set that is authorized, then we cannot deduce anything about the secret S. So we have an all or nothing reconstruction of the secret. Okay. Let us define a key policy attribute-based encryption scheme. We have 4 algorithms, of which the first 3 are randomized, and the decryption, of course, has to be deterministic because we want to be sure of the decryption. In the setup, we compute the public parameters and a master key. The master key will be used by the authority to distribute the decryption keys. Then we have encryption that takes a message M, a set of attributes S that describe the ciphertext, and with the public parameters, we can compute the ciphertext CT. Key generation, to give a secret key, a decryption key, to a user, The authority that has knowledge of the master key MK takes an access structure that describes an access policy suitable for the user and computes a decryption key that works only on ciphertexts that satisfy this access structure. Finally, the decryption takes a ciphertext that is described with a set of attributes S, a decryption key SK that is associated to an access control structure A, and the public parameters. Then the decryption outputs the original message M if and only if the set S is authorized for the access control structure A. Okay, let us see how we can construct this scheme. For the setup, we need a universe of attributes, we call U, and a generator G of a bilinear group G1. Then the authority chooses uniformly at random an element gamma in ZP that we want different from 0 and 1. But if we choose it uniformly at random, the probability of it being different from 0 and 1 is overwhelming. And we choose an element Zi for each attribute in the universe. Then we publish the parameters as gamma, capital gamma, that is the pairing of G with self elevated to small case gamma. And for each attribute in the universe, the element capital Zi, that is G elevated to small caps Zi. Then the master key is simply the collection of these secret exponents. So the gamma and the Zi, one for each attribute. Okay. Let's see how we can generate a secret key. We take an access structure and convert it to a linear secret sharing scheme. So we have a matrix M and a labeling function rho, where M is an L times N matrix over ZP. Then the authority chooses uniformly at random a vector V in ZP to N, and we fix V1 equal to gamma. Then we compute the vector of shares lambda, multiplying the matrix times this vector V, and we obtain the share lambda I. Then the decryption key is the collection of the elements Ki, that is G elevated to lambda I divided by Z rho I, that is the exponent Z corresponding to the attribute that is labeled by the labeling function rho of the matrix. So for each row of the matrix, we compute this element using the share and tying it to the attribute that corresponds to that row of the matrix. The encryption is fairly simple. We take the plaintext as an element of G2. Then its encryption for a set of attributes S contained in the universe is the following. First, we put the description of the set of attributes. Then we have the payload, C first, that is M multiplied by capital gamma to the C, where C is an element of ZP chosen uniformly at random. Finally, we put for each attribute in the set the element Ci, that is Zi taken from the public parameters, that is the public element associated to that attribute in the universe, elevated to the same exponent C. So basically, we're using the public parameters to encrypt the payload with this element that is randomly mapped into the target group G2. And then to allow decryption, we provide these elements associated to the attributes in the set. Okay. For the decryption, let us consider the matrix M with the labeling function rho, that is a linear secret sharing scheme associated to our S key, the key that we want to use to decrypt. Let us suppose that S, the attribute set for the ciphertext that we want to decrypt, is authorized for this access structure. Otherwise, we cannot decrypt anything. Then, given the matrix and the set, we can compute, we can find a subset of S, such that, and the corresponding coefficient Wi, so that if we would have the shares lambda I, then we will be able to reconstruct the secret gamma by interpolating these shares with the coefficients Wi. Of course, we do not have these shares lambda I in the clear, but they are embedded in the secret key. So we can use these coefficients to decrypt anyway. In fact, we simply do this operation. We take the payload C first and divide it by the multiplication of the pairings of the elements from the key Ki with the element of the ciphertext C rho I. Note that we have to use the correct element of the ciphertext so that the attributes correspond, basically. Then we and all of these pairings are elevated to these coefficients Wi that we computed in the equation 6. We can see that the decryption is correct because the payload is M multiplied by capital gamma to the S, with S is a random exponent. But the Ki are G elevated to lambda I, where lambda I is the share of gamma, divided by Z rho I, and the elements of the ciphertext are the Z rho I elevated to the same random exponent as used in the payload. This is by definition of the ciphertext. Then the Z rho I are defined simply as G elevated to the small z rho I. Then we can use the bilinearity of the pairing to take every exponent outside of the pairing. Then we can see that the Z rho I simplify because we have once on the denominator and once on the numerator. And then we are left with S, lambda I, and Wi. Then we can exploit the properties of the exponent to transfer this product as a sum in the exponents. So we have S multiplied by the sum for I in capital I of Wi times lambda I. This is exactly the interpolation of 6. So this is exactly small gamma. Then, by definition of capital gamma, this is the pairing of G with itself elevated to gamma. So we have both on the numerator and denominator the pairing of G with itself elevated to S times gamma. So they simplify, and we can reconstruct the original message M. Okay, how do we evaluate the security of such a scheme? We describe the selective set security model. In this security model, we have an adversary which declares the set of attributes that it wishes to challenge upon in advance. Then the challenger runs the setup algorithm, initializes the authorities, and gives to the adversary the public parameters. Then the adversary issues queries for private keys corresponding to access structures of its choice, but with the limitation that this access structure cannot authorize the target set S, because otherwise it will be extremely simple to win the game. Then we have the core phase, that is the challenge phase, where the adversary chooses two messages of equal length, M0 and M1, and gives them to the challenger. The challenger chooses one message at random and encrypts it with for the set authority S that was chosen in advance. Then the ciphertext is passed on to the adversary. The adversary can issue again queries for access structure of its choice with the same limitation that the set S cannot be authorized for these access structures. And eventually, the adversary has to output a guess of which of the two messages had been encrypted in the challenge phase. Our security result is that if an adversary can break the scheme, that is, win with more than negligible adversary the security game that we have just described, then we can build a simulator that can play the decisional bilinear Diffie-Hellman game with non-negligible advantage. How can we prove this theorem? Let's see a sketch of the proof. Let us suppose that there is a polynomial time adversary that can attack the scheme in the selective set model with advantage epsilon. Then our goal is to build a simulator that retains advantage half of epsilon. Since epsilon was non-negligible, half of epsilon is also non-negligible. So we would disprove our thesis, and because we suppose our assumption is that the decisional bilinear Diffie-Hellman game cannot be solved with non-negligible advantage, then we have proven our theorem. Okay, to construct the simulator, we take in a bilinear Diffie-Hellman challenge. That is the generator and the four elements G2A, G2B, G2C, and T. And we embed these values in the public parameters and the answers to key queries. In particular, we force the choice of gamma to be A times B. So the simulator will not know the value of gamma, but we will be able to compute the values by exploiting the pairing and the elements G2A, G2B, and G2C that we construct. And we encrypt our challenge, that is the MB that we choose in step 4, using the target element T. So we simply multiply the message MB times T. With this trick, the simulator outputs a valid encryption if and only if this challenge contained T in the form pairing of G with itself to ABC. So we have correctly simulated the attribute-based encryption scheme if this is the case, and so we can retain the full advantage of our adversary in this subcase. But because we are half the time in this case and half the time in the other case, we retain an advantage that is half. Okay, there are some upgrade that we can make to a key policy attribute-based encryption scheme, but we do not have enough time, so I prefer not to adventure in these topics. So if you have any question, I'm here for you.